Good afternoon all. This is Mustaq, and today will be our session 6, and most of the session I'll be talking about the thermodynamic properties of nanomaterials. So I'll be starting with temperature dependence on. Temperature dependence on size of the nanoparticle. 2. The composition dependence on again the size of the nanoparticle. And 3. The melting point. Sorry, it's not. Yeah. The temperature, the melting point dependence on the size of the nanoparticle. And this one is the vacancy concentration, not temperature. So first one is the vacancy concentration dependence on nanoparticle. Another one is the composition. The composition dependence on the size of the nanoparticle. And finally you have the melting point temperature dependence of the nanoparticle. So let's start with the mole fraction of vacancies. So I will write it like this. The mole fraction we have, suppose if I write delta G or G total for the system for the formation of vacancies will be equals to the G bulk for the formation of vacancies and G surface for formation of vacancies. And we know how to find the mole fraction of vacancies in the bulk. So if you assume we have NV vacancies and N atoms, and there is also this assumption like the number of equilibrium vacancies in a bulk material will be very much less than the total number of sites, the total number of atoms. So total number of sites will be NV plus N. So, and we know we also derived the configuration entropy in the previous session. So the configuration entropy part will be NV ln XV plus N ln XN, and this will be an empty quantity. We will have an R here, and according to our assumption number 1, if NV is finally if NV is very much less than 1, then Xn will be approximately to 1. So this term will be 0. So finally we are arriving with XV equals to exponential minus delta H by RT. If you are talking about per mole, or we can write as KT if you want, if you are writing for per vacancy. So this is for bulk. Now what about for the surface? So I think what the extra term will be added at minus delta H. Now that will be equals to minus delta H by RT, where delta H is new delta H, so that I am representing as delta H dash. So that delta H dash will be delta H plus 2 gamma by R, or 2 gamma Pm by R, molar volume, atomic volume if you want to take. So if you substitute there, then XV equals to X, and this part will become bulk. So X bulk times exponential plus 2 gamma Bm by RKT. Now again from Taylor expansion, exponential minus x will be 1 minus x, approximately equals to 1 minus x, and this will be according to curvature x bulk of 1. For convex surface we have more number of vacancies when compared to bulk, so write like that, RKT. This is 1, and for concave we will have minus sign in between. So if you have a powder particle like this, let's say it's a powder particle, two powder particles are touching each other, then what happens? So the vacancies will move from here to here. So x mole fraction of vacancies in concave is less than mole fraction of vacancies in concave surface will be less than bulk equals to less than convex. So that is how we prove it. Now next, let's go to this one, the temperature dependence. So how do we define the temperature dependence again? And why I'm just repeating again, because to make sure you are familiar with the derivation to solve the assignment problems. So the next part is this one, right? Temperature dependence. So again, if I assume this is my nanoparticle and it starts melting, suppose it forms a very thin layer around it, very thin layer when compared to delta, it is R. So let's say assume R is greater than delta. Then this is our solid one, this is our liquid, okay, liquid phase. Then again from Gibbs-Duhan equation, where VdP minus SdT, V alpha, this alpha, if I take this alpha, this is beta, and it will be beta minus S beta. So delta V dP equals to delta S dt. This will be approximately equals to dP by dt, and delta S, it is delta H by Tm times delta V. So let's go to the next slide. Now dP by dt equals to delta H Tm times delta V. This will be equals to, and this will arrive at delta P equals to delta H by Tm into delta V. This will be equals to del dt. And if we assume there is a node dependence, and also let's suppose V beta minus V alpha, and if you are assuming that there is a large amount of nanoparticles, so V beta is greater than V alpha, so this will be V beta approximately. Then this dP will be change in pressure, and we know that change in pressure is 2 gamma by R, that is equals to delta H by Tm V beta T minus Tm. This will turn out to be T equals to Tm, so it is not. This will turn out to be 2 gamma TM B theta by R delta H. So T is a function of R and how it is inversely proportional. So if R tends to infinite, I mean if you're talking about the bulk surface or the flat surface, then T will be equals to Tm for bulk materials. Now if you go on decreasing R, then T shifts or T decreases. Now the composition relation. Just like I mentioned before, where T decreases with Tm. Now, for example, if I take copper nickel phase diagram, suppose this side is my pure copper, and this side is my pure nickel. Because copper has a less melting point on compared to nickel, and copper nickel forms a very nice isomorphic diagram. So copper has less melting temperature than nickel. So this is for bulk. Now what happens for less radius nanoparticles? I mean the nanoparticles, what happens to the melting temperature of nanoparticles? As I have derived before, the melting temperature decreases if you go on reducing the size of the nanoparticle. So what happens to melting point of both copper and nickel? They go down. So they just shifts the whole phase diagram to downwards. So let's say if I try to draw for this is for copper, sorry, this is copper, this is nickel, and this is my bulk. What happens to if I decrease the size of the nanoparticle? This also decreases. This is, for example, let's say R is approximately equals to 20 nanometers. Then what happens to 10 nanometers? R equals to 10 nanometers. So this is how our melting points defines the phase diagrams. Now the whole explanation I have done before only about this part, because we are not considering any alloy. We are only talking about pure nanoparticles. So this region, the pure copper region and the pure copper region, pure nickel region, and those equations that we have derived only hold for these two points. Now what happens if you have an alloy? So how that will change? Let's say how the composition changes with the size of the nanoparticle. For example, I have a beta phase, and from, let's say, it's a supersaturated phase, and if I give it enough temperature and enough time for the diffusion of atoms, then there is a formation of alpha phase in the beta phase. So what happens to that? How the size of the precipitate will be affected by the composition, of how the composition will be changed by the size of the precipitate by form. Now let's suppose we have a eutectic phase diagram. This is my alpha. This is my beta. This is eutectic. This is a liquid. This is alpha plus L. This is beta plus L. This is alpha plus beta. So now let's assume the beta has very much less solid solubility. For example, beta has very less. Solid solubility. what does that mean? Suppose in beta phase has variables yes solubility of A. That means beta cannot take a high amount of solutes in its phase. So then what happens? If we draw the G versus X, real G versus composition diagram, it goes on positive. So this direction or the opposite direction is negative. And here we have mole fraction of P. This is my G alpha phase. Which is my G alpha, the free energy curve for alpha. So it has two extremes. One is for the free energy of A in alpha phase. That means the pure A with alpha crystal structure. But now here, the free energy of pure B with alpha crystal structure. Suppose alpha crystal structure is FCC. So beta crystal structure is BCC. I'm just assuming the free energy of pure A in alpha crystal structure, pure energy of pure B in alpha crystal structure. Then again, what about free energy curve of beta? Then because beta has very less solid solubility, so it should curve like this. Now this point will touch somewhere there. It will have the pure. So let's talk about this point where the beta G curve touches at xb equal to 1. That will be our free energy of pure B in of beta crystal structure, and the other extremity will touch at free energy of pure B, pure A in alpha crystal structure. So I have derived for the chemical potential equation how on which terms the chemical potential of B depends on if we take about regular solutions. So from the quasi-chemical model, I derived for delta H, and I will derive for the configuration entropy. So the mu B equals to GB plus, suppose if I talk about like alpha phase, alpha plus omega term and minus xp whole square plus rt log xp. Now what will it will become? Mu b of alpha. Suppose if I write for mu b beta, right? What should I write? Let's write for maybe alpha itself. GB alpha, that will be equals to minus GB alpha, and we know the xb is less than 1, then this will turn out to be 0. So if xb approximately equals to 1, because beta has very much less solid solubility. If I take that, xp equals to 1, then this will be mu times 1 plus RT xp. And if I see the free energy where it cuts the xp equals to 1, the curve will look like this, right? So this will be my, and to find the equilibrium we draw the tangent between two curves. Again, I have explained in last sessions. So let's say this is my tangent and where the tangent touches the xp, that will be mu b in beta phase. If I take it again, take it like that, and where this curve touches, that will be gb in beta phase. So, and we know at equilibrium maybe alpha equals to maybe beta, and that will be approximately equals to gb beta. Now this will be written as alpha plus alpha xp. RTL and XP, and oh sorry, this is have less solid solubility, right? So this should be goes to 0, then that shouldn't be 0. Yeah, it should go to 0, and it will become log XP equals to delta X by RT, and XP equals to exponential. Here, let me add few slides. This will be where did we arrive? X b, right? Xb equals to exponential minus delta G by RT. Now this is for a bulk law. Now what happens if we are talking about the nanoparticles? And if we are talking about nanoparticles, there is again this excess free energy, and that excess free energy will be coming from the surface energy. And how you relate the free energy to surface energy? Easy, by this given equation. Again, I have derived before, please go and see it. If you're not comfortable with it, then that will be delta P times V. This is delta V equals to 2 gamma by R. Delta P will be 2 gamma by R, which is fixed equation. Now, what happens to it? So, it decreases or increases? It increases the delta G, right? But why? Sorry, why? Because the surface energy is a positive term. So what happens? Xv equals to exponential minus delta C by RT times exponential 2 gamma A R. And this will again will be equals to related to bulk. So xb and xb, see, let's say a nanoparticle, so bulk times exponential 2 gamma by R. Now again, from tangent expansion, exponential of x will be approximately equals to 1 plus x. So xb nanoparticle equals to xb bulk 1 plus 2 gamma by R. So this is how our composition changes with respect to R. So yeah, this is a relation for the composition. Now let it write in a more simplified way so that you can understand it more. So this is 1 xr divided by x infinite. For r equals to infinite, I mean the bulk material, that will be 1 to gamma v by RT times R. R is the size of the nanoparticle. From this, we can see that there will be quite large solubility differences can be arise for particles less than like 1000 or 100 nanometers. So like 100 nanometers, we can see the difference. There is a large difference in solubilities when compared to bulk. So this is the third relation of how the mole fraction, the composition of a nanoparticle changes with respect to bulk in atomic composition, where the beta phase has very sparingly solubility, very sparing solubility, or very low amount of solubility of B. The low amount of solubility of A in beta phase. So that's the third relation. Now let's move on to the final let's move on to the how the surface energy changes. Now let's say this is my material and I have grains here. Let's say I have grains here, and this region is my grain boundary region. Now why I'm explaining is this, because this relationship shows there is a difference in solubilities of beta when compared to the bulk phase, where we have seen, let's say for example, if we take values like 2 gamma Vm by RT, like let's say the 2 gamma Vm by RT equals to 1. Let's say we assume our values of surface energy, molar volume, universal gas constant, temperature will be resulted or will be divided in such a way that we get a value of 1. Then what happens? The mole fraction of nanoparticle, or the composition of the nanoparticle divided with the composition when compared to bulk, equals to 1 plus 1 by R. So from there we can see how the R changing will change the composition of a nanoparticle. Now let's go to material where we have a grain bound grain. Suppose our grain is a nanoparticle and our grain bound. So how do we define a grain and grain bound? So in grain we have a very ordered arrangement of hardness, but when compared to grain boundary, the grain boundary doesn't have an ordered structure. Sometimes you have disordered or semi-ordered structures. So let's say we have a grain boundary with a disordered structure. Now, what happens? So because we have a grain boundary, there is an interface, interfaces. What do you call it? An interface is called when there are two phases separated by a boundary, and then we call it as interfaces. And for example, if I have two grains, say phases in alpha, then you can simply call it as a grain boundary, which separates the two phases. Now what's our next goal? Next goal is to learn how free energy will change with the composition of both bulk and our, for example, let's say our grain has a composition of X, and our grain boundary has some other composition. For example, I'm just taking X direction. Now how the free energy or the surface free energy, that means the free energy of the grain boundary, the surface energy of the grain boundary will be affected by the composition of the grain. Now, let's derive it. Let's say I have a, for example, let's say, no, let's first derive the free energy. Free energy equation. The free energy equation is dg equals to v dp minus s dt. Now, this is for the closed system, where there is no exchange of matter. Only we are talking about a cold system, where everything is happening in a system, in a closed system. So that we take this equation. Now what happens if there is an open system? Then what happens? If you're talking about open system, then there is a transfer of matter or the flow of matter, we can say. Then what happens? Then we should write it like dg equals to v dp minus s dt plus sigma I equals to 1 to m mu I dm. And I have also, and I mentioned many times what is chemical potential. Chemical potential is nothing but, when suppose I have a system, I have A particles and I have B particles. Let's say they are equimolar, it doesn't matter if you take different compositions. Let's say I have A particles and B particles, or let's say A atoms and A type of atoms and B type of atoms. So it's a binary of one. You know why? The chemical potential term came. We can write it just like in the free energy term, but the thing is, let's say if I have A and B mixture, now let's say there is no like it's just a mechanical mixture. Then what happens? The total free energy of the system will be total free energy per mole. If I take GT by number of moles, then it will be equals to mole fraction of A times GA plus mole fraction of B times GB. If I draw G versus XA, it will be a straight line, right? Let's say if I give GA as the molar energy of A as 5 kilojoules per mole and GB as 10 kilojoules per mole. What happens? So GT will totally depend on XA. So for example, if I take 1 by 5 mole, 1 by 5, suppose if I have a mole fraction of A as 0.2, then it will be 0.2 times 5 plus whatever the other part. That is 0.2 is 1 by 5 by 5 is 0.2, right? Yeah. And xb equals to 4 by 5. Yeah. Let's write like this. It's 0.8 times 10. What is our GT? GT will be 0.2 times 5 is 1 and 0.8 times 10 is 8. This is 9 kilojoules per mole. Now see, GA doesn't depend on mole fraction. It's not a function of mole fraction. It is just a constant value. But what happens if there is an atomistic mixture, like let's say have AB mixture? Let's say there is no mechanical mixture, right? Where, so for example, there is a metallic bond. Then what happens? The free energy change. Let's say, so here, when we are talking about mechanical mixture, the free energy is constant. Then what happens? Dou Ga by dou X, take G will be equals to 0. Now, what happens in alloys? If I add small amount of A atoms, then this is not equals to constant, and so therefore we introduce the chemical potential. What does chemical potential mean? Chemical potential means change in free energy of the system when small amount of A moles are added. That is our chemical potential. And if you're talking about mechanical mixtures, simply will turn out to be just G naught of A. We can say that pure form of pure K, right? This will turn out to be delta Ga by Na, no, delta Ga, N times Ga naught by Na will cancel. This will turn out to be G naught of A. So far so good. So now let's move on to here, this equation. Let's write that equation. Dou Gi, no, let's not Dou Gi, let's dg per mole. Okay, I'm talking about. Let's say just dg dash. That will turn out to be bdp minus sdt STP plus I equals to 1 to n, and this n runs to number of alloying elements, so number of elements present in the phase, times mu naught I, the chemical potential of that species in that phase, of any ith species in that phase, times dni plus, if there are any other terms, if there is a can say there is any other work done, like electrical work that is performed, you can write it. And this is for bulk. Now, what will happen if I write it for a nanoparticle or a very small phase? Shouldn't say very small phase, a very small sized phase. Then what happens? Then the surface energy terms comes. How do you write the surface energy term? This that will be equals to VdP minus SdT plus I equals to m I dni. Now, the surface energy term, the extra term that comes in will be sigma I equals to 1 to m gamma I dni. Now, what does that mean? That means the surface energies of all the phases. Suppose if I have a cube, I have 6 phases, then I add all the surface energies of 6 phases. this, and if I have some other irregular shape, add all the surface energies on it. That's how it is. Now let's talk about let's talk about Gibbs to Him equation. Gibbs.
What's that? सर ने बोला कि मेरी क्लास है 5 बजे और होने के बाद मुझसे मिलना। ये भाई साहब चले गए और हमसे बोले गए कि मंडे से आएंगे, फ्राइडे को नहीं आएंगे। सर बोले फ्राइडे क्यों नहीं आएंगे? सर हमको क्या पता। उसने बोला मंडे से आएंगे। नहीं ठीक है सर, मंडे से आएंगे। हमको क्या तो ना नहीं बोलता, बोले थे सर ने। हाँ ये बोल रही है कि अगर मैंने सोच लिया कि तुम लोग वो कर रहे हो, बात कर रहे हो फालतू का, तो मैं निकाल दूंगा उसे, छोड़ूंगा नहीं।
मीटिंग चल रहा है।
हाँ मीटिंग चल रही है। अच्छा पढ़ा रहे हैं क्या? राइट।
That gives to her equation. Now, what does Gibbs Duhem equation does? Now, it's a very unique equation that describes a change in relationship between two dependent properties. For example, the chemical potential depends on the number of particles in the system, and this Gibbs equation will use the relationship between the dependable properties, or you can say extension properties. So for example, now in this case, let's say I describe this as equation number 1, for example, or for this derivation it is equation number 1. Then what happens? Let's derive this. So our dg dash is vdp minus sdt. Let's say I'm talking about a binary algorithm. Then mu a dna plus mu b dnp. Now, if I write it not in differential form but in algebraic form, then this g will be vp minus st plus mu I or mu a n a plus mu b n p. Now if we're talking about the constant volume system, so I write it like dp equals to 0 and ds equals to 0. Let's take out this part. Right? This will be equals to mu a n a plus mu b n b. Now dg will be equals to mu a dna plus mu b dnb plus na d mu a plus nb d mu b. This is what it is. Now comparing this equation to equation, let's say this is number 3, comparing equation 1 with equation 2 with equation 3, this term is equals to these two terms. Now, what happens to this term? This term will be equals to 0. From this equation we can give the relationship between the chemical potential or the extension properties. If we don't assume the dp is equal to 0 or ds is equal to 0, or sorry, it's not ds, it's dt. Yeah, dt equals to 0, and if we take out this term, then they again will appear in this Gibbs-Duhem equation. So the Gibbs-Duhem equation, if I write it like this, or if I write it for per mole, then it will be equals to xa d mu a minus xb d mu b, and we know d mu a equals to rt xa, sorry, it's dxa by xa, right, for ideal solutions, and d mu b equals to rt dxv by xv. Now substitute that here. Let's not it will again become what do you call the Raultanian, it will show the Raultanian behavior, so let's not take that. It will be again the same as the Raultanian. We will derive the Raultanian law. We can derive the Raultanian law from here. If you substitute the chemical potential is equal to just I wrote here RT dxa, let's say. So let's not do that here. That thing. So d mu a equals to xv by xa d mu v. What is d mu a? Right. Okay. That is RT log, I should write this right, RT log A, activity of A, then differentiating will return out to DAA by activity of A. This will be equals to RT activity of A, activity of A, XA, RT, the activity of B, cancel. A will be equals to 6v by xa. Now dAB, the mole fraction of A goes to 0. Now this is a relation how we actually find the activities of any component. Let's do the activity of A. Let's say this is, I'm writing it this for alpha phase. This whole will be an alpha phase. This will be an alpha phase. So this is for an alpha phase. So that's how we derive or we calculate the activities of any components in the solid solution from the Gibbs-Stephan equation. Now we know the importance of Gibbs-Stephan equation. Now let's find how the free energy will change. Let's start with this. We have G equals to free energy, total free energy of system equals to G bulk. G excess plus the surface area term. If we are talking about a nanomaterial, what if you are talking about the bulk then if you are talking about the bulk, excess term is neglected because for bulk materials the surface energy is neglected because it is very much less when compared to the free energies, the bulk free energies, and the error will be like 1%. So we mostly avoid it. Now this is for the regular solutions. Now what about for ideal solutions? The ideal solutions and the bulk materials, GT equals G bulk. That's right for nanomaterial. I'm writing it as an alloy. Let's say binary alloy. Now binary alloy, but for bulk material, and it is regular solutions, and this is derived from quasi-chemical model. How everyone followed my previous sessions, they can know, then you can understand what how we derived G axis from quasi-chemical model. Now this is for ideal solutions. Ideal solution, ideal solid solution, right? Solid solution and bulk material. Right? Yeah. Now let me add few more slides. Let's go back to previous equation. So now as we are talking about grain and grain boundary, let's assume that grain is a bulk material and grain boundary is a let's say the grain region as a bulk material and grain boundary as a surface one. So then let's write it free energy for both the grain and grain boundary. That will be equals to dg what I'm going to do is I'm going to represent grain as a bulk. So I'm going to give a bulk notation for grain. So it will be B equals to V B plus S B dt plus I goes to 1 to n. I goes to 1 to n mu I dI. And because we are considering as a bulk, we are not considering the surface properties like surface energy, because we are only interested in the grain, the bulk ratio. So now let's write the same equation for the grain boundary. Now because the grain let's write as ZB, and because the grain boundary has a base, so what we are going to do is we are going to define the surface energy for the grain boundary now. So dg grain boundary will be equals to v grain boundary dp plus grain boundary dt plus 1 to m mu I. Let's write it as chemical potential for bulk grain boundary. Sorry, it shouldn't contain m. Sorry, it shouldn't contain area. It should contain number of particles, right? Because it is chemical potential. Yeah. Now it is. Let's say it is for grain boundary bulk plus the extra term that is added, that will be equals to 1 to n and gamma di. Then again writing gives you. So this is our equations for the change in free energies for the grain boundary and the grain, which we are assuming as a bulk material. Now, if the grain and grain boundary are in equilibrium, then the change in free energies of both the phases must be equal. So what does that mean? If you write it mathematically, that is dg of bulk, or we can call it as grain, will be equals to dg of grain boundary. Now, if I write my the Gibbs-Duhem equation for 1, let's say if I write Gibbs-Duhem equation for 1, let's say there is no change in pressure or temperature, there is no change in pressure or temperature, again there is no change in volume, and these terms will go out, and we are remained with for bulk. For grain, the Gibbs-Duhem equation will be results in sigma I equals to 1 to n ni bulk d I b equals to 0. This is for 1. Now again writing a Gibbs equation for 2, that will result in I is equals to 1 to n and I grain boundary times, let's write it clearly, and I grain boundary mu I boundary plus a boundary times d change in surface area for the grain. No, it's not mentioned grain boundary because we are only considering the surface potential for the surface itself, so this will be equals to 0. Now, therefore, now comparing uh, this, let's say this is a 3 equation over 3, now comparing 3 and 4, so both are 0 and both can be equated, then that will turn out to be I equals to, let's write it here, I equals to 1, 2, and well, call we are talking about boundary, then we are B equals to sigma equals to 1 to m ni GB times d mu by GB plus a GB this one. So if we put this set of equations over here, this will turn out to be sigma I equals to 1 to n d if I take minus sign for now, then this will turn out to be ni GB GB b whole divided by area of main boundary differential of free then we know from common tangent in free energy versus composition curve, let's say I draw the free energy versus composition. This is my free energy. This is my composition. B. Now, what happens? So, let's say we have two phases, alpha and beta, which are in equilibrium. Let's draw the free energy versus composition for both alpha and beta phase. Let's say this is my alpha phase and this is the beta phase. Now, if this is for G alpha, this is for G beta, and let's say G alpha and G beta ideal solutions for simple understanding. Even for regular solutions or subregular solutions, you will get the chemical potential is same of any element in both the phases at equilibrium. So let me derive it for the ideal solution. Now we know G alpha equals to, let's write it for G total first. The G total equals to G alpha XA plus G beta XB. Now we know G total for ideal solutions equals to XA G naught A plus XB G naught B plus RT XA ln XA plus RT XB ln XB. Now, what is GA? GA equals to G naught of A plus RT ln this can be equated to chemical potentials. So yeah, mu A equals to G naught of A RT, where I can say mu B equals to G naught of B RT, where I can say. So we can write it like both the guys if you wanted, like G equals to mu A xp plus mu B xp rather than gx or gxp. When compared to it, now what happens, d mu A equals to, this will turn out to be 0, then RT 1 by xa times dxa, this will, and mu B RT 1 by xb times dxb. Now these two must be equal. Suppose I am talking about alpha phase, then what happens? So 1 by xa dxa equals to 1 by xv dxv. This will be equals to ln xa ln xv plus c, and because if you start deriving it will turn out to be 0, so ln xa ln xb. Now if you are talking in terms of activities, then activity of A will be equals to activity of B. So this is how the activities are equal for different elements in a single phase if the two phases are in equilibrium, right? Sorry, it shouldn't be, yeah, it should be for beta phase, right? Sorry, it should be for beta phase. Chemical potential of A. Yeah, so d mu here, it should be right, d mu A. Yeah, this one is correct. So this will turn out to be, it shouldn't be xb. Let me write it again. It's a mistake. Let me make it clear. And see, when two phases are equilibrium, just like I have said before, the change in free energies of the phases must be equal. If I don't write like this, if I want to write it for a specific element, I can write. So the change in free energy for both the phases must be equal when the alpha and beta phase are in equilibrium. So if I write for dg alpha and dg beta, then if you are talking about a single element, then this will turn out to be, yeah, dga so this is for changing chemical potential for A in alpha phase and changing chemical potential of A in beta phase. So when this becomes equal, then the activities will be equal. Again, we can relate chemical potential to activities. Mu equals to RT ln G naught of A plus RT ln A. Let's move on to where it was here. Yeah, we were at here. So we were deriving for how to simplify this equation. Now we know that when two phases are in equilibrium, the chemical potentials of elements in the both phases must be, the change in chemical potential of both phases must must be equal, or even you can say the chemical potentials must be equal. So the chemical potential of A in beta phase. We arrive to a very important relation. Now, let me write this equation again. Minus sigma I equals to 1 to m d mu I gv and I gv minus d mu I bulk and I bulk a gv equals to dA, change in free energy, differential of surface free energy. Now from this equation, if our grain and grain boundary are in equilibrium, let's say bulk grain and grain boundary are in equilibrium, then the chemical potentials of those elements in those phases should be equal. So d mu ith element in grain boundary must be equal to ith element boundary, then this equation can be simplified to minus I equals to 1 to m d mu I gv times ni gv minus ni bulk to d divided by gv. Now let's write what is, we know what is the differential of chemical potential. So, and because we are writing for like B, so let's assume the activity of the in phase obeys Henry's law. When we know Henry's law, activity of any component, if it is a dilute solution, then activity of that component will be equals to the dilute solute will be equals to constant times mole fraction of that I in that solution. So let me write it more clearly. It should turn out to be 2p of I is equal to Ki times mole fraction of I. So it should write B, it should be I. Erase it properly. Okay, this is how it happens to be. Now, and this will write differential of pure. Right. Let me write it. Pure grain boundary plus RT log Kb xb plus RT log Kb. On differentiating this term will turn out to be 0 because they are constants. And will be equals to RT on differentiating this will turn out to be xb times dxb. Now let's assume like, okay, let's substitute it there in this equation. So let me write this equation again. Equals to 1 to m I equals to 1 to m d mu I gv times ni substituting that into that equation, d may be equal to RT 1 by XA GV, and can write it as a bulk because we got the bulk composition. So let me write it as XA bulk and DXB DXA bulk times Ni DGB minus Ni B divided by area. So there's no dash here, so area equals to doing it. And let's put these let's put some of these terms to constant, and because if you are talking about alloy, binary alloy, then I will be max to 2. So I'm putting everything, this term to be constants, and that will come to be minus A RT XA bulk into DXA of bulk. So now again, this, let's say this tau A will approximately depends on simplifying, approximately depends on XA of plane boundary because the number of atoms times thickness T times the density. Let me write it. XA of mole fraction of A grain boundary T thickness of grain boundary D density of grain. Now let me add few more slides. We are near to end of the derivation. So on substituting them here, I equals to say nanomaterials, it's a bulk times DXA bulk times RT thickness times rho. integrating both sides. That's integration. So it's a GV RT times T times rho integral. There is this part. Integral. So it's a bulk. Now the surface energy will be changing from let's write the integrals. I mean the boundary conditions. We can say first and final conditions, initial and final conditions for right hand side. That will be xa equals to 0. No, it shouldn't be 0, right? It should be pure. XA will be 1 times XA equals to XA. This will be surface free energy at XA is equal to 1, pure alpha phase, then surface free energy at XA equals to some value of XA. Then this will turn out to be free energy at any composition equals to not, you can just represent free energy not as a free energy, surface free energy of a particle XA equals to pure A. Let me remove this one. This will be equals to minus XA G RT T E we missed a negative term here. Yeah, there is a negative term, so this will be negative. So finally have a negative term here. T, this will be rho, the density times normal. Let's say, well, this is another relation that gives the relationship between the free energy, the surface energy, not free energy, surface energy of a composition, of a respective composition A, which is XA of a nanoparticle, when compared to the surface energy of a pure A nanoparticle. So this is our relation. So let's go back to our initial slides. Let's see what we have discussed so far. Slideshow. Yeah. So we first started deriving the three relations. How the mole fraction of vacancies depends on the size of the nanoparticle, and again the composition of the newly formed nanoparticle in a certain phase, how it depends upon R, how the solubility changes with R, again how the melting temperature changes with R. And for the first equation derivation we used the total free energy will be the bulk in surface free energy, and for deriving the bulk part, we used there are two parts of entropy. One is the thermal and one is the configuration entropy. So we used the configuration entropy here, and we can even invert, or we can even include the thermal entropy part here. So that the delta H will be turned out to be delta H minus T delta S which is thermal. There is thermal. You can include the term there. We will get an extra term, but again, it only talks about the bulk, so it will come out as the mole fraction of accuracy is suppose mole fraction of accuracy is, let me write it as R accuracy is, yeah, that will be bulk times this, and depending upon the curvature, like whether we have a let's say concave or convex, the vacancies concentration will varies with respect to bulk. So for example, if I have two powder particles here, they're in contact, so they form sintering. Why the formation of sintering? Because this is the convex surface, and convex surface will have more number of vacancies. Sorry, the convex surface have okay. Let me correct this. So concave will have more number of vacancies, right? Yeah, it should be, because the powder particles comes here, then the vacancies should move where, then this relationship should be changed to this one. Yeah, let's remove this. Increase increase less. Yeah, so concave should have more number of vacancies compared to convex, so that if this is our concave and this is our convex, so from concave there is movement of vacancies, from convex there is movement of atoms, because for a substitutional diffusion we need the movement of atoms, right? So this is our first one. Let's move on to the second one, where we derive how, sorry, for the third one, right, where how we derive how the melting temperature will change. We applied the Gibbs-Duhem equation, and we even shown how the phase diagrams change with respect to the size of the particle. And the second one was how the composition changes when new phase forms with respect to the size of the precipitate. And here we assume they have alpha phase and beta phase, and we assume that beta has very much less solid solubility of A. So from there and this relation is important because we approximated this term. See, if we see it very like closely, let's assume that this curve touches the tangent. We have two terms. One is GV beta, and we have chemical potential of B in beta. See, there is some difference, but as we are assuming very less spreading solubility, and we are approximating it that these two terms are equal, then from there we arrive to this equation, how the mole fraction, the solid solubility changes with respect to R. And then we were interested in finding how the free energy, or sorry, not the free energy, the surface energy changes of a grain boundary. The surface energy of a grain boundary changes with mole fraction or the composition of A for any element. We first wrote the free energy equation, the most basic form of the equation. Then here we are. Then we wrote then I explained a little bit what is chemical potential. Then we came to know about what is Gibbs-Duhem equation, how it is useful in finding the extension properties like activity, mole fraction. So not mole fraction, the activity, chemical potential of any elements. So finally we arrived to this equation. From there we calculated how the activity changes with the mole fraction. Then we came to what are the terms that are involved in a nanoparticle binary alloy, and binary alloy which is a bulk material, and which is a regular solution which has a regular solution. and it's not, yeah, it's a regular solution. This is a regular solution. And then again, how what is the total free energy for ideal solution. Then again we then again I little bit explain how, not how, what happens when there is a equilibrium between two phases like alpha and beta. Yeah, and from there we derived. From there we used Gibbs-Duhem equation to solve. So we wrote it for the bulk or the grain, and we wrote it for the grain boundary. We finally out to this equation, but once and then I showed how to like how do we came to conclusion that the activities are equal, or the mole fraction, or sorry, no, not mole fraction, the chemical potentials are equal in a phase. Sorry, of an element in two different phases. So from there from there we then derived how, so not derived, how this equation can be this complex equation can be equated and when it's simple, and then we assume this sorry from there we wrote the chemical potential for grain boundaries. Then we assumed some constants. Then we wrote constant as tau a, and then we wrote how tau a depends on different terms like mole fraction of grain boundary, thickness of grain boundary, density of grain boundary, and then we finally arrived to this equation how the surface energy changes with mole fraction of the composition of A in our grain boundary and B. So that's it for today. Thank you. If you have any doubts, you can post in the channel or the YouTube comments where I can get to your where I can get your answers as soon as possible. So please, if you have any doubts, let me know in the comments. Thank you.